topic I'm going to discuss, and there's going to be two parts. One is more on the history of quantumness, how it came about, and then the second part is more specifically on the phenomenon of superconductivity. The classical treatment that everybody knew at that time gives you a completely wrong answer. So Planck was quite desperate. He didn't know, and then basically he guessed. So he did what he called later an act of desperation. He guessed this fact, gives you a completely wrong answer, completely, but it gives you infinity instead of finite. That's as wrong as it is. So this was utterly guessed by Max Planck. He didn't know where it came from. It turned out the birth of superconductivity. Almost zero is an understatement. It's so zero that if you take a loop of superconductor and you create a current circulating in it, it would stay there for a good part of the life of the universe. Whereas the better conductors that we know, like silver or copper, the time is about a microsecond. So this is as much as zero exists in nature, really. Quantumness of superconductors. Superconductors are quantum in many senses, but one way in which they are quantum is that there exists a gap or a step between the superconducting state and the so-called normal state. This explains actually a lot of weird properties of a superconductor, including something that is very similar to the photoelectric effect, which we already discussed.
It gives me immense pleasure and I think a lot of honor to invite Prof. Paolo Radaelli for our session here today. He is a Dr. Lee Professor of Experimental Philosophy, which is basically physics, at the University of Oxford. He is also a professorial fellow at Wharton College, and he has had a very illustrious career working at various top-notch institutes for research in condensed matter physics across the world, within United States, in France, and as well as the United Kingdom. And he is very well known and among the topmost researchers in the field for condensed matter physics. He has innumerable publications discussing about how various aspects of quantum physics, of statistical physics, or of semi-classical physics can actually be used to describe materials and very fascinating behavior, which is quite uncommon in our day-to-day materials, can be realized in very special circumstances. He has worked extensively with X-rays, with neutrons as probes to actually understand and investigate these materials and understand the phenomena that is undergoing in these material systems. He has a very profound honor of being the Knight of the Order of Star of Italy, which he received just a few years ago. And he has just recently completed his tenure as a head of the condensed matter physics department, as well as the associate head of the physics department in University of Oxford. So these are his credentials, but I've had a lot of privilege to work with him directly, and I foresee working with him over many, many more years, and I have gotten an opportunity to interact with him, and I noticed that he is not only an amazing researcher who has very beautiful holistic understanding of physics, but also he is an extremely amazing educationist. And as soon as I discovered that, I was like, I have to invite him for this session here, and he very kindly obliged and was willing to join for the session, so I'm very grateful. Paolo, please, I would like you to lead your session. Just one insight on what Prof. Paolo is going to be sharing with you guys. You have seen a very vast expanse of various aspects of quantum physics in our discussions over the last 2 or 3 days. Prof. Paolo is going to suggest two aspects. Historically, he's going to discuss all the aspects that came slightly before the whole launching of the photoelectric effect. Some of you had asked the question, where is the constant H coming from? You'll have a slightly better understanding of that in the first section of his talk. And then he talks and he jumps the discussion that we have done, and he's going to talk about superconductivity, where you've seen a little bit of that discussion in the session on quantum computing, as well as with Dr. Prof. Venki yesterday when he was talking about the applications of superconducting qubits, etc. Superconducting circuits like squids, etc. So what is exactly the quantum phenomena happening there? You will see a little bit of that as well. So really, Paolo will help us ground our understanding of quantum physics in reality. Okay. With that, without further ado, please, Paolo, go ahead.
Thank you very much, Hariom. Welcome to you all. I hope you'll enjoy the lecture. And Hariom has already given you a hint of what I'm going to talk about. Okay, so that's the topic I'm going to discuss, and there's going to be two parts. One is more on the history of quantumness, how it came about, and then the second part is more specifically on the phenomenon of superconductivity, which you already have encountered in previous lectures. So science is as old as humanity. It doesn't really have a birthplace. As soon as people started to look up at the night sky, they started investigating and wondering, what is that about? If we could identify a workplace for science, it's not going to be in Europe. In fact, until recently, Europe was a rather backward place, Western Europe, with respect to other places such as the Eastern Mediterranean, Persia, India, or China. However, something happened in the beginning of the 17th century to change this, and this has a birthplace and a birth date. And this man is mostly credited to be the father of what had happened next. What happened was the creation of what is known now as the scientific method. The scientific method is an odd mixture of things that existed before: Greek philosophy, mathematics, as well as observational science. And all this gave rise to the language that we still use today when we talk about science, at least mostly. This man's name was Galileo Galilei. He was born in Pisa in 1564. And you'll certainly know him in many contexts. He's the first person who observed the satellite of Jupiter, for example, the first person to propose the principle of inertia. And I want to quote something he wrote in 1623, which captures the essence of the scientific method. He wrote in a book called Il Saggiatore, which means the Assayer, and he wrote the following: philosophy is written in this great book that is all the time open in front of our eyes, I mean the universe. But you cannot understand it if you haven't learned beforehand to understand the language in which it is written. It is written in mathematical language, and its characters are triangles, circles, and other geometrical figures, without which it is impossible for a man to understand a single word. Without these, it is like wandering vainly in a dark labyrinth. So this is what he was writing then, and this is probably what we still believe now, at least if we are working in physics. It is essential to understand the mathematical language. Otherwise, you're just wandering and you're basically lost. And you should not be deluded if you want to become a physicist, which I very much hope you all will, that you can have a qualitative understanding of what physics is about. This is a bit delusionary. You have to understand mathematics, so spend most of your time learning mathematics, and you also understand physics. So the outline of this lecture is precisely how the idea of quantumness emerged from classical ideas and measurements. And what I want to show you is how this didn't emerge because there were some strange phenomena that people discovered all of a sudden, but because they look back at phenomena that were known from the age, the dawn of time, and they could not put them in this mathematical framework in which Galileo was talking about. These mathematical, there was a mathematical necessity to describe these phenomena, and they couldn't just fit it. They couldn't understand how they could do that. And this is how the idea of quantum came about. So what is the phenomenon I'm talking about? It's the phenomenon of radiation heat. So if you take something that's really hot, you know that, of course, if you touch it, you're going to get burned. But you're going to be heated. You get radiant energy from that object, even if you're not touching it. And this is mainly due to what we know today as radiation heat. So if you heat up a piece of iron, for example, here shown on the left, and you put your hand next to it, you get a lot of heat. The other thing you notice is that depending on how much you heat things, you get different colors. And this is nicely shown in the picture of the left. There's a molten substance here that is heated over some coal, and the molten substance is red and the coals are yellow. So the color of objects changes depending on their temperature. This has been known for millennia by all the culture in the world. So around the beginning of the 19th century, so the 1800s, people started to try and understand quantitatively how this heat energy is related to the temperature. And this is the timeline of the things I'm going to talk about today, which led to the understanding of how this comes about. The story starts before the 1800s, and in particular starts in the end of the 17th century, when people understood that light is a wave. And here's Christian Huygens' picture there, who's the first person who understood that. And then the main action is the middle and the end of the 19th century. And these are all the people, or most of the people associated with it, at least the one I'm going to talk about. You will see that they have different things in common. They're all men, and they all have a mustache or a beard. So this is, except for Jeans, who doesn't have a beard, but everybody else has either mustache or beard. So it is a common characteristic, and you have to come to terms with the fact that all these people were born within 1,000 kilometers of Brussels. So this is something that is part of our legacy. Many of them were born in Germany or in Austria, where a lot of the action takes place. But of course, many important figures like James Maxwell, he was born in England and in Scotland actually, and many others. So it was only a bit later that non-European persons became important, and the first one is Gibbs, and he's the first great American physicist. But of course, later on, many other people from all over the world came about it and contributed to physics. And here I'm just showing a few important early Asian contributors to physics in a very, very substantial and, as they say today, non-tokenistic way. It is a really important contribution coming from Asia. Now, women is a little bit of a different story, and many of you I learned are women, and women only came to the fore at the beginning of the 20th century. And this is a very nice illustration of the state of affairs in about 1931. Is a famous photograph taken on the steps of Via Panisperna's palace in Rome in the first nuclear physics conference, 1931. Basically, there's a lot of men, mainly famous men, of which I have indicated a few, of which you might know the name: Niels Bohr, Arnold Sommerfeld, Guglielmo Marconi, Enrico Fermi. And there are two women, one clearly visible, Marie Curie, and the other one is a little bit obscure, Lisa Meitner. So these two women, actually, they were not incidentally there. They were fierce characters and very central to the development of nuclear physics. They were the two women that produces all the nuclear isotopes that all these other men were using or they were theorizing about. So they were controlling the whole of the early nuclear physics, these two women. And Enrico Fermi, whose picture there, got so frustrated because he couldn't get these. He only came later to be interested in nuclear physics. And he was frustrated, he couldn't get these samples from these women. So he ended up inventing the neutron technology as an alternative. This is telling you how important the contribution of these women were. So if you're a woman and you want to become a physicist, you certainly have very good role models there. Okay, but back to our story. So the first thing that these people try to understand, and this is circa mid-19th century, was the actual total amount of heat that was given up. So if I go back to my picture here, how much heat in total is given out by a hot object? And how does that heat depend on temperature? So heat is a quantity that by then they knew very well how to measure. They measured it in calories, or they could measure it in other units. Today we would measure it in joules. And the more things are hot, the more heat they give out, total heat. Okay? And this again is something that has been known from the dawn of time. So some precise measurements were done by John Tyndall in 1864 from a platinum filament, which was heated by electric current. And then Joseph Stefan in Germany used this data to determine empirically the so-called Stefan relation. So that the total emitted power, which you would measure in watts per square meter, okay? So total power is watts, total energy would be joules. So watts is joules per second per square meter. So the total amount of heat depends on the total surface of the object that is emitting. And that total power is proportional to the fourth power of the temperature, of the absolute temperature. Okay, so absolute temperature, room temperature is about 290 Kelvin. Okay, so that's what Stefan determined empirically, based on previous accurate measurement of this power. Later on, a bit later on, Ludwig Boltzmann determined that this law, which now is known as the Stefan Boltzmann Law. Ludwig Boltzmann was a fellow citizen of Joseph Stefan. They were both Austrian. They were part of the Austrian power. Boltzmann, who is a great figure in the 19th century's physics, determined that this law is actually necessary based on Maxwell's equation. Maxwell's equations were determined by Maxwell a few years before, and then Adolfo Bartoli in Italy determined that discovered the consequence of radiation pressure, the fact that radiation actually exercises a pressure, so light actually has a pressure, and then based on that concept, Ludwig Boltzmann in 1884 determined that the Stefan Boltzmann law is a necessity arising from Boltzmann equation. Okay. However, Boltzmann equations do not predict the constant that is in front of it. The constant that I indicated here is sigma. Okay. So J, as I said before, is watt per square meter. The fourth power of the temperature is Kelvin to the fourth power. So what is this constant sigma? Okay. This is not predicted based on Boltzmann equation. Okay. So this is a very strange thing. It would have been astonished from a man of the 19th century to think about this constant sigma. First of all, it has very strange units. Okay, so it has units watts per square meter per Kelvin to the fourth power, which is really weird. Okay, then the other thing that they would have considered is that this must be some kind of fundamental constant. They already knew, and this was discovered by another physicist known Kirchhoff, that not all the objects emit the same amount of power, because the objects that are reflecting, like if you have a piece of silver, it emits less power, but if you have a black object, it emits precisely the same power, regardless of the nature of the object. Okay, so this sigma constant is a universal constant of some sort, right? So it actually, the value of this constant is 5.67 times 10 to the minus 8 in these strange units. And it's equal for all bodies that are black, so-called black bodies. Okay? So is it the fundamental constant of nature, or is it derived constant from other constants that existed before? That's what they would have asked themselves. Okay, so what constants were known in the mid-1800s? Well, okay, people knew the speed of light. The speed of light was first determined a long time before, in 1676, by a Danish astronomer called Ole Rømer, based on the phenomenon that is known as stellar aberration, essentially astronomical observation. Okay, so that was known, the fact that there is a constant speed of light 300,000 kilometers per second was known. And of course, this is a very important quantity in Maxwell's equations. And then the other constant that was known was the so-called Boltzmann constant, K 1.38 times 10 to the minus 23 joules per Kelvin. This will play an important part in our story, but essentially connects the temperature of an object with the energy of the microscopic particles that form the object, essentially atoms and molecules. People had a kind of vague idea of what they would be in the mid-1800s, but they knew the value of this constant, at least approximately. So from these two constants, you cannot get anything that has the dimensions of the Stefan Boltzmann constant. So it seems indeed that the Stefan Boltzmann constant is a constant of nature, no matter how weird that constant is. Okay, so this is where Stefan Boltzmann law rested in about 1884. And at about that time, people started to do very accurate measurements of the power in each of the colors of the light that is emitted by a black body. So a black body, you can split the light of a black body using a prism, for example, as shown here, right? And then you can imagine, you can isolate each color in the prism, in the spectrum of the prism, in the rainbow coming off the prism, and you can try and determine the power, the emitted power from only that color. This is a very difficult measurement. If you think about how you would do it in 1880, it's incredibly difficult. And in fact, in Germany, they constructed a whole institute, which at that time was called the PTR, or Imperial Physical Technical Institute. And a lot of the work for that institute at that time was devoted in determine the power in each of these colors. So what is depicted here is the main picture is this picture here shows the emitted power as a function of wavelength, as we would measure it today. At that time, it was much more difficult to do a measurement like this. The center part of the spectrum is the visible light. The part on here on the left is the ultraviolet, and the part here on the right is the infrared. Both properties, where both infrared and ultraviolet light have been known since about 1800. That there exists invisible radiation that contains power. This has been known since that. And if you imagine to divide this spectrum or this curve in little slivers, each representing a color, either visible or invisible, you can measure the power in each color. Okay, so essentially the area of the violet would be the violet power, the area in the yellow would be the yellow power, and so on and so forth. Okay, so the people, particularly at this PTR, but also elsewhere in England and in other places, they started to do very sophisticated measurements to try and determine these curves. I'm going to show you in these curves in a different way. Instead of plotted as a function of the wavelength of the light, I will plot them as a function of frequency, okay? Because it's easier to understand the equations in frequency rather than in wavelength. So you all know that the product of the wavelength and the frequency is the speed of light, or at least I'm telling you now. And this is from Maxwell's equations. Okay. So, and I'm going to do another thing that is some of you may think is really mathematical. I'm going to use logarithm, right? So, because for a reason I'm explaining in a second. So, for those of you who may not have encountered logarithms is a very convenient way to span very wide extents of orders of magnitude compressed in a single scale. So, the logarithm of 1 is 0, the logarithm of 10 is 1, the logarithm of 100 is 2. So essentially count the number of 0, and the logarithm of 0.1 is -1. Okay, so I'm going to use logarithms, and I'm going to use frequencies. And these are the same curves, exactly the same curve as before. So power per unit color, if you want, or per unit frequency, plotted on a logarithmic scale in both frequency and intensity or power. Okay, so in the figure here on my left, I show a few temperatures, and you can see the central part is the visible light. The part on the left, in this case, is the low frequency part, that is the infrared, and the part on the right is the ultraviolet. Okay, and here curves are plotted for different temperature. So one thing you see here, that the maximum power, the frequency at which maximum power occurs, increases with temperature. And this accounts for the first picture I showed, which is the fact that the color of the light emitted by a heated body shifts with temperature towards, from red to yellow to green to blue at a very high temperature. Okay, so in the sun, the temperature of the sun is about 5,000 Kelvin, and it is more or less green, yellow-green. Okay, so that's the first thing that we need to look from this curve. Now, the curve here on the right is a modern, of course, is a modern curve because it contains much more radiation. It has the X-rays in it, it has the radio waves in it, but it gives you a more sort of global impression of what these curves look like. So first of all, if you look at the low frequency curve, this part here, and each curve represents a temperature, you see a series of parallel lines. Okay, these parallel lines in this plot indicates that the power is proportional to some power of the frequency. So, and this power actually is 2. So the power is proportional to the frequency squared. This is what these parallel lines indicate. And again, this is a mathematical consideration based on the shape of these curves. But then you'll see they reach a maximum and then they crash down very fast. Okay? And the maximum grows with temperature, and in fact grows linearly with temperature. So the maximum frequency, the maximum emission, occurs at a frequency that is proportional to the temperature of the body. Okay, so this is what you deduce by looking at these curves. Now, there are profound mathematical consequences of this that would have been clear also for somebody in the 1800s. So if you think about representing these curves as a function, okay, these are as a function of temperature and frequency, the first thing you notice is that here, that what we call the integral of this curve has to give you the Stefan Boltzmann law. So if you take the area under these curves, for example, the area under the 300 Kelvin curve, that's known as the integral of the curve. This area is proportional to the temperature, and the proportionality constant is the Stefan Boltzmann constant. First thing, okay? But then the other thing is that in order for you to get, so to the 4th power, so I should have said sigma to the 4th power. And then the second part here is that, sorry, let me just correct that. Okay. And then the second thing is that from purely mathematical consideration, in order to get your proportionality to the 4th power of the temperature in the integral and the proportionality of the maximum to the temperature, you have to have a form that is indicated here, right? So which this has to be the general form of that function. Okay, so this seems a bit strange that you can deduce this just by these two considerations, but please trust me that this is what they also in the 1800s were able to figure out. And from this general form is known as Veen's displacement law, and Veen it was again a physicist working at this institute that worked out this so-called displacement law based on this mathematics that I have talked to you about. So let me explain how it would work. Wilhelm Veen in 1893 worked out this law. Okay, so this again is a plot of these curves. Now no longer on a log scale, but on an ordinary scale. at different temperatures. So let's say you start from the 5,000 Kelvin temperature, okay? So I color that curve, okay? Now, in order, I want to get from that curve to the 8,000 Kelvin curve, okay, which is the top curve. What I do is I do two things. First of all, I stretch it by 8/5, which is the ratio between 8,000 and 5,000. And then I stretch it upwards by the cube of 8/5, 4.1. And I get exactly the curve at 8,000 Kelvin. So essentially all these curves is the same curve with a bit of stretch. This is Veen's displacement law, okay? However, okay, this is very good, but we still don't know what this function is. So this mystery function, f of the ratio of the frequency and the temperature, is a function of the ratio of the nu over t. There has been a lot of debates for many years about what that function might be. So Veen himself, a bit later, proposed the form that this function should be e to the minus a constant, a, times the frequency of a temperature. Now, this actually turns out to be wrong, but as we see in a second, but it was a very important step forward because, again, based on mathematical consideration, it enables you to deduce something very profound about this function. So, first of all, the form that Veen proposed was e to the minus a nu over t, where nu is the frequency. A is a constant. So what is A? Is it a new constant of nature again? This is really strange. You know, we already had the Stefan Boltzmann constant, and here's another constant cropping up. Also, the other thing that is important is that A multiplied by nu over t has to give something that is without dimension. So it cannot be meters or Kelvin or joules. It has to be a number, okay? Because anything that is within an exponential has to be a number. So this A nu over t must be a pure number, no units. So one very easy thing you can do is to multiply the temperature by the Boltzmann constant, which gives you an energy. So this kT is an energy. And then in this case, you get another constant instead of A, which is H, which has very simple units, joules times second, okay? So this Veen surmise, this is the real fundamental constant, but this constant is not called the Veen's constant. Now, if you have this constant H, okay, you can rework your Stefan Boltzmann constant sigma as a function of H, and you can express it in this form, which looks complicated, but in fact is really simple. And this K, this kappa constant here, which I circle, is actually pure number. Okay, so you don't need another constant for the Stefan Boltzmann law. The constant H, which was worked out from Veen's law, is sufficient, okay, to explain both phenomena. In fact, this pure number happens to be 2 pi to the 5th power over 15, which is, again, looks like a strange number, but it's really simple. So the new fundamental constant is H. Its value is 6.62 times 10 to the minus 34 in international units, joules per second. We often use this quantity to measure energy at the atomic scale is the electron volt, which is the energy that is given by a 1 volt battery to an electron if you just pass it through the 2 poles of the battery. So sometimes this constant H is expressed in these electron volt per second. As I say, this constant is not called the Veen's constant, but it's called the Planck constant. So what did Max Planck have to do with this? So Max Planck was another German physicist who was working on the data from this Imperial Institute, and he was trying to understand whether Veen's law actually worked, and he figured out that it actually doesn't quite work. So here is the ER curve at about 6,000 Kelvin, and the true curve that fits the data is the blue curve. And the dashed line is the Veen curve. The Veen curve works well at high frequency, where the exponential, so-called exponential tail, as shown here, this part here, but it doesn't quite work here in this low region. The green curve I'll talk you about later. Okay, so this is the Veen curve kind of fails there. So Planck was quite desperate. He didn't know, and then basically he guessed. So he did what he called later an act of desperation. He guessed this function. So this function, instead of being the Veen form, which e to the minus h nu over kt, he proposed this other form, 1 over e to the h nu over kt minus 1. Okay, and this was utterly guessed by Max Planck. He didn't know where it came from. It turns out that the two curves are the same at high frequency, which explains why essentially they coincide. They become essentially almost identical if you in the limit of high frequency. Okay, so it turns out that the new proposal by Planck explained all the data from the Imperial Institute perfectly. Okay, however, Max Planck had no clue of where this came about. However, he made another very important guess. This is Planck formula, full formula, where the prefactor is a numerical factor. And it turns out that the integral of this is, I don't know why I keep forgetting the fourth power here, is the Stefan Boltzmann Law. Okay, so before I do that, so at this point, Planck made what we know today as the quantum hypothesis. So that this constant h, which we know today as Planck constant, was related to the fact that energy could be given to the system not continuously, but in quanta. And he guessed this on the fact, not necessarily on the form of his law, but on the idea, even on the exponential function. So he knew that if you have a system of objects to which you can give energy in discrete amounts, that system will display an exponential behavior as shown here. Okay, he didn't believe very much in statistical physics, which was then at a very early stage, but he knew enough to be able to say, okay, there's got to be something discrete, something quantum, and quantum means a discrete amount, a given amount. Okay, so he proposed a quantum hypothesis. Systems such as light can be given energy in quanta. Okay, and this quantum is related to the Planck constant. So it's h nu is the quantum of energy you can give to the system. Now, there's a very interesting treatment that was done a few years later by these two gentlemen, James Jeans and John Riley, which is a classical treatment. It doesn't involve the constant h, and treats radiation as occurring in a cavity. So you can think about a black body as a cavity. So the best black body even today is a furnace with a hole. Okay, and they said, okay, what if light in the cavity is in the form of standing waves, like waves on a string? Okay, so we can think about counting these, how many possible waves exist in the cavity, and they counted them as to be this amount, okay, per unit frequency. And then you think about giving energy to these standing waves, and they guessed that the energy should be kT per standing wave, where K is something we already know is the Boltzmann constant. So this is something that was well known at the time, that if you have a system in thermodynamic equilibrium, in thermal equilibrium, the energy per particle is in fact 1/2 kT per degree of freedom, and for the standing wave it would be kT. So from this very classical treatment, there's no H in this treatment, they get this law, okay, which is known as the Rayleigh-Jeans law. Now, if we compare, so that would be the intensity of the light. This is the total energy of the light in the cavity, and it's very easy to get the radiated energy from the black body. So if you compare the Planck's law here to the Raleigh's law here, they look quite different, don't they? Okay, this top has the Planck constant in it. The bottom one doesn't have the Planck constant. But you will notice that in the limit of low frequency, the Planck formalism and the Rayleigh-Jeans formalism are the same, or become the same in the limit of low frequency. Now let's plot them, and you could see how they look like. So again, the dashed line here, the purple line is Veen, the blue line is Planck, and the Rayleigh-Jeans is green, the dotted line, okay? So the dotted line fails completely. It has the so-called ultraviolet catastrophe. So it works fine at low frequency, but it's completely wrong. It gives you infinite energy at high frequency. So the classical treatment that everybody knew at that time gives you a completely wrong answer, completely, but it gives you infinity instead of finite. That's as wrong as it is. So why does it fail? Why does it fail? So it fails. It could have failed for many reasons. They could have guessed many reasons, but the reason why it fails is that equipetition fails. So it fails because you cannot give the equipetition idea, so the fact that that relates the Planck constant to the amount of energy per macroscopic body, only works if you can give it infinitesimal amount of energy to the system. But if you quantize that energy, it fails. And this is what explains the discrepancy. So now, actually, based on what was known at that time, you would have guessed the Veen formula instead of the Planck formula. So Planck formula remained a mystery for another about 10 years. And it was finally explained by these two people. And this is the only non-European person in the story, Bose, and this is well-known Albert Einstein. So actually it was Bose who proved it. And a very funny story. So Bose was a lecturer at the University of Dhaka, and he gave a lecture on the black body radiation. And he worked out some calculation whereby he got the Planck formula, okay? And then he wrote to Einstein and said, I don't know enough German. Actually, he knew German very well. He knew lots of languages, but he didn't know enough German. He felt he didn't know enough German to write a paper in Germany. And he wanted to publish in a German journal. So he asked Albert Einstein help, and Albert Einstein immediately understood what he was on. And then he basically worked out photons, okay? So what we know today as Bose-Einstein formalism of statistics is what we apply to photons, and the quanta are photons. And Albert Einstein, when he finally met Bose, he said, but do you realize you have worked out a completely new quantum statistics? And Bose says, no, sir, I don't know. I never knew the other statistics. I just worked it out mathematically, okay? And this is how we know today that quanta of light are photons. So it turns out that now we know a lot more, and we know that also particles in a box are quantized, but the quanta are much, much, much smaller. So orders of magnitude smaller, and this is why equipetition works, at least at ordinary temperatures. Okay, so now the whole story is complete. Second part of the lecture is on superconductivity. So this is really a weird quantum phenomenon that people discovered just a little later. And in fact, this is the first piece of data that showed the existence of superconductivity. The man shown here is called the Kamerlingh Onnes, and he's the first person who measured a superconducting transition. And by superconductivity, what we mean is that a metal completely loses its electrical resistance below a certain temperature. So Kamerlingh Onnes was a professor of experimental physics at the University of Leiden, and he founded a large laboratory to study things at low temperature. And he started to measure resistance of a lot of different things at low temperature. And at some point he measured mercury, which is we all know is liquid at room temperature, but is solid at low temperature. And this is the entry in his diary, which in Dutch reads something like Kwik na genoeg nul. So kwik is quicksilver, which is mercury. Mercury almost zero. Okay, so that's the curve that he later published, 8th of April 1911. That's the birth of superconductivity. So almost zero is an understatement. It's so zero that if you take a loop of superconductor and you create a current circulating in it, it will stay there for a good part of the life of the universe. Whereas the better conductors that we know, like silver or copper, the time is about a microsecond. So this is as much as zero exists in nature, really. Can you still hear me?
Very clearly.
Okay. So very quickly, I'm going to tell you the story of superconductivity after coming on this. For many years, people discovered more and more materials that were superconducting, and as the materials became more complicated, they were able to raise the temperature, known as the critical temperature, by up to about 20, almost 30 Kelvin, 27 Kelvin, I think, was the maximum. And these first group of superconductors are still used today in an MRI machine, for example. If you go for an MRI scan, that's based on superconductors of this kind. A very important milestone came in 1957 by the discovery of so-called Bcs Theory, from the names of three American physicists, John Bardeen, Leon Cooper, and John Robert Friffer, who presented a comprehensive theory of superconductivity, of which I'll tell you a little bit later. About then, a few years later, another physicist, American physicist, chemist and physicist, Bernd Matthias, discovered a lot of new materials that were superconductors and proposed the following ideas to help people looking for superconductors. So the so-called Matthias rule. Materials have to be cubic or have high symmetry. They have to have high density of electronic states or high density of electrons. They should not contain oxygen. They should not be magnetic. They should not be insulating, or as far away from insulators as possible. And also he suggested stay away from theorists. Because in spite of the fact that Bardeen, Cooper, and Schiffer has explained superconductivity, they could not predict which materials would be superconductors. So when I was a student, 1986, something quite extraordinary happened. This man, Alex Müller, discovered a material which was superconducting initially at 30 Kelvin, but quickly very similar materials became superconducting over 40 Kelvin, and perhaps a year later, 90 Kelvin, above liquid nitrogen. And these are today known as high TC superconductors. Now, these materials, so he won the Nobel Prize the same year, actually, for his discovery. He was on the completely wrong track. So he discovered these materials entirely by chance, looking for superconductivity, but based on a theory which today we know to be wrong. So that's the story after that. That's the critical temperature from the time he discovered the material, the first material, which had formula lanthanum, barium, copper oxide, down up to about 2000 later on, where the highest temperature that is today known to superconduct at ambient pressure was discovered, was based on mercury. Now, the interesting thing about these new materials is that they are not cubic. They are very far from cubic. They have low density of electronic states. They are oxides. They are magnetic. And they are very close to being insulators. So all the materials rules were cancelled, except for one: stay away from theories. That still holds. Anyway, later on, many new families of superconductors were discovered based on iron. And more recently, people were able to obtain superconductivity essentially at room temperature, except at very, very high pressures. So I think the record is 260 Kelvin, which in some places on Earth, in some seasons, is room temperature, in very simple materials containing hydrogen at extremely high pressure. Okay, so I'm going to focus on one aspect of superconductivity. You will hear many other aspects. So the wave nature of superconductivity as a macroscopic wave function, that's very important. And you will hear about how that can be used for quantum computation. But today I'm going to focus on only on one thing, which is the quantumness of superconductors. Superconductors are quantum in many senses, but one way in which they are quantum is that there exists a gap or a step between the superconducting state and the so-called normal state. Okay, so you have to give a certain amount of finite amount of energy to a superconductor to get electrons out of the superconducting state. So this explains actually a lot of weird properties of superconductor, including something that is very similar to the photoelectric effect, which we already discussed, in the way they respond to heat and light and many other things. But I'm not going to talk about that. I want to focus only on the gap and how that gap is related to the zero resistance property of superconductor. Quick, Naego, Ogen, Null. So it turns out that actually Cooper is the three people that I showed you before. Cooper is the guy that proposes the gap. He was a graduate student at that time and proposed a very simple model based on relatively simple quantum mechanics, which showed the existence of a gap. And then this was developed in a full-fledged theory by Veen, particularly by Veen, John Veen. Okay, so in order for you to understand, or at least glimpse at the mathematics behind this zero resistance state, you have to understand one thing, that electrons in a metal, electrons are charged, negatively charged particles, and are unlike particles in a box. They're very different from the way particles in a box, for example, gas in a box, would behave. So you remember Galileo's circles and triangles. You're going to use a lot of circles in the next few slides. So the way I want you to think about electrons in metals is based on this picture. Think about a crowd sitting in a theater with empty seats around it. It's a very strange way to think about metals, right? So what are these people representing? So I'm going to draw a circle on them. This circle depicts the color of the ticket that these people have. They went to this theater and they have a ticket, each of a different color. The color of the ticket is the energy of the electrons in the metal. Okay, and the distance from the center of the circle represents their velocity. So if you connect the line between where a person is to the center, that indicates the direction and magnitude of their velocity. So that's a metal at low temperature. Now we're talking about velocities here that are extremely high. So people at the edge of the crowd, near the empty seats, at low temperature, have velocities of about 0.5% of the speed of light. Okay, extremely high at zero temperature. This is extremely strange and comes about because of a principle proposed by Wolfgang Pauli, known as the Pauli extrusion principle. Okay. Now, the people in the theater can move seats. Okay, this process in metals is known as scattering. But in ordinary metal, they have to conserve energy. So they can sit in another seat, but the ticket has to match the color of the seat if you want to follow the analogy. Okay, so they can move around. They normally do that when in real metal, when the electron collides with something in the metal, like an impurity, for example. But they have to conserve energy. All right. So let me just depict this in a schematic way. So this depicts the crowd in the red circle at low temperature in the theater, and this is the color of their tickets. And this depicts a metal without any current. Okay, so as you can see, the velocity, there's so many people with left velocity, that right velocity or top velocity and bottom velocity. So there's an average velocity of 0, although the velocities themselves for each of the electrons are extremely high. Okay, now let's think about giving some current to this metal. Okay, so we do that by creating an average velocity or a collective velocity. So we shift that crowd to one side. Okay, that represents a metal which carries current. Okay, and I want to show you how is it possible for that current to decay in a microsecond or so in a very pure metal. How is it possible for that current to decay? Through scattering, so through people moving around into seats of the same color. And this should be an animation. So now each person has moved to a different seat, but with the same color as the original seat. And you could see now that the people redistribute in different places. And the end of the process, which is this, well, you can carry on, but I'll just show you in an intermediate stage. You can see now the velocity are much more balanced. So the average velocity is 0, but there are lots of empty seats in between. And this represents temperature. When there are lots of empty seats in between, it means that the metal has heated up. And this is exactly what happens if you take a cold metal and you flow current through it. The current will decay and the metal will heat. You know, you'll all know in light bulb that this happens. Okay, so this is in a normal metal, not in a superconductor, how current decays. Okay, through electrons moving around and conserving energy, whilst not being able to sit in a seat where somebody else was already sitting. And this is Pauli exclusion principle. They're excluded from sitting where somebody else is sitting. Okay, this is why they have such high velocities. Okay, now what about the superconductor? So the superconductor, there is a gap. Okay, so this is the gap that separates the superconducting state at low temperature from the normal state. So in keeping the analogy of people in the crowd, in order to stand up from where they're sitting, they have to pay a price. So instead of going to a seat with the same color, they can only go to a seat with a color that is closer to the center. In this example that I'm drawing, they lose 4 colors. So the green can only move into this kind of orange color, the yellow into the light blue color, and the blue into this pink color. Okay, so they can scatter, but they have to pay this gap in order to do that, and therefore they can sit back down, but in a seat that is closer to the center of the crowd than it was before. So let me show you how this produces superconductivity. Okay, so by the way, the existence of this gap, as I said, was predicted by Cooper on a very simple model based on pairing. So electrons marry up or pair up in what are known today as Cooper pairs, and the energy of pairing up is the gap, in a sense, in a simple term. Okay, so let's take our superconductor. This is a superconductor without current, and this is the superconductor with some flowing current. Now you can see that the electrons at the edge are blue, but the blue will have to go down to the pink, which is inside the crowd. So there's no empty seats there. So there's no scattering possible. So that current, if the electrons have this collective velocity, that current persists forever. Electrons cannot scatter, cannot reduce their collective velocity by scattering. Now let's see what happens if I increase the velocity. Okay, so now some electrons at the edge of the crowd are yellow here on the what I'm telling you is, oops. Let's see if I can do that. Yeah, so the edge of the crowd, then some electrons here are yellow, but the yellow electrons will have to go down. So I wanted to previous one. Okay, this one. Okay, so some electrons are yellow, like this one here, but the yellow will have to go down to the blue, light blue here, and there's no empty seats in the white blue, so it's still superconducting. However, if I go down one step further, I reach what is known as a critical velocity. In a critical velocity, now the yellow here can go down to this blue. Okay, so I have the possibility of scattering. And then if I go to a even higher velocity, I have a lot of possibility of scattering. Okay, so the conclusion is that scattering cannot occur unless electrons collectively or on average have a minimum critical velocity, which today is related to what's known as the critical current of the superconductor. The superconductor can only carry so much current, right, whilst remaining superconductor. About that current, above that velocity, or above that current, the electrical resistance above the current is finite, but below that current, the electrical resistance is precisely zero, and precisely, okay, is to within a fraction of the life of the universe. Okay, so that's the end of the story. I want to end my story with, I started with Galileo, an Italian physicist, the father of the experimental method. There are lots of challenges in science, there are lots of challenges in education. So if you want to become a physicist, if you want to become an educator, either at the university level or at any other level, you will face a lot of challenges, a lot of cultural challenges. However, in my opinion, we should heed here the advice of another Italian scientist, early Italian scientist, much before Galileo, about a century and a half before Galileo, who also was looking at nature, was looking at the star, and he, Leonardo da Vinci, and he wrote this famous sentence: whoever gazes at the star does not turn around. So look at physics, keep being persistent on physics, study your mathematics, and don't turn around. Thank you very much.
Thank you, Paolo, for that beautiful presentation. I think